Here are the sample problems for class 17 of Math 117. And the first one is to state and prove the three fundamental laws for conditional expectation. So I'll start with the first one, taking out what is known TOEIC. And here are the assumptions. You've got a product of two random variables, x times y, and that's integrable. And furthermore, one of these random variables, x, is measurable with respect to our sigma field G. Since I'm assuming that the sigma field is generated by a countable partition, this means simply that x is constant on each set G sub n in the partition. And what taking out what is known says is that if you're computing the expectation of the product of two random variables conditioned on a certain sigma field G, and x is constant on each set G sub n, then you can just take it out. And what you get is x times the expectation of the other random variable in the product, y, conditioned on G. And here's the proof. Let's consider some little omega in our sample space. This omega is going to be an element of G sub n for some n in the partition. And that's what makes this proof dead easy. Let's call it omega sub n. And then work out the conditional expectation. What's the formula for conditional expectation? Well, effectively, you treat the set G sub n in the partition as if it were the entire sample space. In computing the expectation of x, you just integrate over G sub n, and since x is constant, doesn't matter which omega sub n in G sub n we pick, this is just a constant that can be taken out of the integral. And then what have we got left? We've got 1 over the probability of G sub n times the integral of y over G sub n. But that's just the definition of the conditional expectation. In other words, conditioning on something that's already constant on each set in the sigma field that you're using for the conditioning has absolutely no effect. Okay, next one. Next one is independence drops out. And so we're considering the situation where the random variable x and the sigma field G are independent. What does that mean? It means that if you think about the level sets of x, that's an event. That's independent of each G sub n in the partition. And what happens in that case is that conditioning has absolutely no effect. That the expectation of x conditioned on g, which officially is a random variable, in this case is a constant random variable. No matter which set g sub n you consider, the value of this is the expectation of x, independent of which g sub n the omega lies in. Okay? How do we prove it? Well, x is independent of the indicator function for each g sub n. And therefore, when I go to calculate the expectation of x conditioned on g for some omega, which I'll call omega sub n to indicate that it lies inside g sub n, by the formula for calculating conditional expectation, I get 1 over the probability of g sub n times the integral of x just over the g sub n part of the sample space. But I can integrate over the whole sample space instead if I simply multiply x by the indicator function that's 1 only on g sub n. And since we know that x and this indicator function are independent, I can first rewrite this as the expectation of x times the indicator function for g sub n, and then use independence to write the expectation of the product as the product of the expectations. So to say this expectation x conditioned on g is 1 over the probability of g sub n times the product of the two expectations, expectation of x times the expectation of the indicator function for g sub n. But the indicator function for any event in the sample space is just the probability of that event. So this is 1 over the probability of g sub n times the expectation of x, which is just a number, times the probability of g sub n. That cancels that, and we're left with the expectation of x. Okay, the last one is the so-called Tower law. And this applies in the case where you've got 3 sigma fields. H is included in G is included in the sigma field F. Now recall what this inclusion means. It means that each H set, each set in the sigma field H is a union of sets that are in G, while each set that's in G is a union of sets that are in F. So H is a much coarser subdivision of the sample space than G. G is in turn coarser than F. And to express this more precisely, I can say each H sub m, because the sigma field H we're assuming is specified by a countable partition, belongs to the sigma field G, and the way it belongs is it a countable union of some of the G sub n. This will become clearer, I would say, in the example that I'm going to do next. Okay, so now what have we got? We're taking the expectation of x conditioned on G. That's a random variable. And when we successively condition that on H, one of the things we have to do is calculate the integral of this over H sub m. Well, what is H sub n? It's a union over the indexes n that lie in some set of integers m of the sets in question. G's are awfully hard to draw. And if I'm integrating over disjoint parts of the sample space, I can just sum over all the sets in the partition that I'm using the integral of the expectation of x conditioned on G over G sub n. But on G sub n, x is a constant. On G sub n, this conditional expectation is a constant that is defined so that it comes out the same as when you integrate x over that same set in the partition. And of course, since H sub m is just the union of these GMs, what I have done in effect is just integrate x over H sub m. In other words, under these circumstances, the effect of integrating x conditioned on G is no different from the effect of just integrating x. In other words, we can forget about G. And we reach our final conclusion. The expectation of the conditional expectation of x conditioned on G and then conditioned on H for some omega sub n is 1 over the probability of H sub n times the integral over H sub n of this already conditioned x conditioned on G but we just figured out what that is equal to. It's 1 over the probability of H sub n times the integral not of x conditioned on G, but instead just of x over H sub n. And that has to be multiplied by, no, that's the definition of the conditional expectation of x conditioned on H for that omega sub n. Okay. Now, let's do a highly contrived example of this, which I think will make things much clearer. This is really a very clever Deneen problem. On the one hand, it's thoroughly stupid and artificial. On the other hand, it explains quite nicely what's going on. So, sample space is 1 through 8. The sigma field is the power set of that. Any subset of 1 through 8 is in the sigma field. The probabilities are 1/10 for the first 4 values, 3/20 for the next 4 values. Those obligingly sum to 1. Random variable x, which we will now write out, has the value 1 on 1 through 4, has the value 2 on 5 through 8. Random variable y has the value 1 on 1 and 5, has the value 2 on the remaining 6 values, and so, of course, x times y is just the product of these two. Which looks like that. The probability of each of these omegas is given. It's 1/10, 1/10, 1/10, 1/10, 3/20, 3/20, 3/20, 3/20. Okay, now we need to work out the expectation of the product xy conditioned on G. So what is G? It's generated by 1, 2, and 3, 4, which means the partition associated with it is 1, 2, 3, 4, and 5, 6, 7, 8. And this has a constant value on each set in the partition, which is the average value of xy over that partition. Well, for 1 and 2, 1 and 2 are equally likely, and therefore on both of these, the expectation of xy conditioned on G, where we're considering G1, set in the partition consisting of 1, 2, is just 3/2. In other words, we're simply replacing xy by its expected value over the set 1, 2. Over the set 3, 4, xy has the constant value 2, so conditioning does nothing. And finally, for 5, 6, 7, and 8, we've got the average value of 3 4s and a 2, which works out to 7/2. This makes it very clear that this conditional expectation is constant on each set in the partition. Now we'll do what looks like this incredibly complicated step of taking that random variable and conditioning it on H. But look at what H is. H is generated by 1, 2, 3, 4, and 5, 6, 7, 8. In other words, H has the property that every set in the partition for H is just a union of some of the sets in G. That G is a subdivision of H. And what the Tower law says is that subdividing further like this has no additional effect when you're computing conditional expectation. So when I condition this on H, I say I need the value for 1, 2, 3, 4, and that's just the numerical average of 3/2 and 2. For 1 through 4, it's equal to 7/4, and for 5 through 8, it's still 7/2. Okay, so we've worked out the left-hand side. Now let's work out the right-hand side. What's the expectation of y? Well, that's just a number. There's a probability of 1/10 of getting 1, plus a probability of 3/10 from 2, 3, and 4 of getting the value 2, plus a probability of 3/20 of a 5 and getting the value 2, plus 3 times 3/20 or 9/20 probability of getting the value 4. Sorry, I messed that up. We're just doing y, aren't we? So this is a 1 here and a 2 here. And with a common denominator of 20, I've got 1/10 is 2/20, and then I have 12/20 from the second term, 3/20 from the third term, and 18/20 from the fourth term. That's 35/20 or 7/4. And what is x times the expectation of y? Well, that's a random variable. It's just 7/4 times x. So I get where x is 1, 7/4, and where x is 2, 7/2. And it all comes out the same. So that's the hard way to do it. Now let's try using these fundamental laws. We can say that G is generated by a subpartition of H. That is, every set in the partition H is just a union of sets in the partition G. And that's the situation where the Tower law applies. And what the Tower law says is simply that if you take xy, first condition on G, and then partition the condition further on H, where each set in the partition H is just a union of sets in G, it was a waste of effort to continue to condition on G in the first place. That's just the expectation of x times y conditioned on H alone. Okay, now look at x. X is constant on H1, on 1 through 4, and it's also constant on H2. And what does taking out what is known say? It says if you've got a product of random variables and one of them is constant on every set in the partition that you're using for conditioning, we can take it out. So, taking out what is known simply says that if I'm conditioning this product on the sigma field H, given that x is constant on every set in H, I can take it out and write it as x times the expectation of y conditioned on H. But now y has been very cleverly devised. Look at the event y equals 1 and the event y equals 2. Those two events are independent of the events H1 and H2. For example, the probability of the event y equals 1 intersect H1, that is of omega equals 1, is just the probability that y equals 1 times the probability of the event H1. And therefore, the final rule, the independence drops out rule, says when you condition on a sigma field consisting of events that are all independent of the ones you've got, I can take this expectation of y conditioned on H and say, because the sets in the partition H are independent of the level sets of y, conditioning on H has absolutely no effect. This is just x times the expectation of y. So, with no explicit computation whatever, we managed to get the same answer. Well, we're back to ancient Egypt. Remember that in exchange for your detective work, Potiphar gave you a call option with a strike price of 38 gold pieces. And this guy doesn't like uncertainty. And he says, I'm in big trouble. If the Nile flooding is starting to fail, this share is going to be really valuable, and I'm going to have to pay a large amount to settle this call option. It's true that if the Nile floods hold up, this option will become worthless and I won't have to pay anything, but I'd rather arrange things so that I pay a fixed amount no matter what. And now I'm going to solve this problem without ever mentioning the probabilities that I worked out in the last class. I'm going to devise a perfect hedge for Potiphar so that no matter what happens with the Nile and shares in Sons of Jacob grain storage, Potiphar shells out exactly the same number of gold pieces. And you already know how to do this. All that matters is we're doing it in 2 steps now. So we're at node B, and the right hedge is to purchase delta sub B shares, where delta sub B is determined by the fact that we get the same revenue if the shares go up to D and if they go down to E. Okay, what happens if they go up to D? Well, we bought these shares, we sell them off for delta B times 150, and then we shell out 112 gold pieces to settle this option. If, on the other hand, the shares stay stuck at 50, well, we can still sell them for 50, and in that case, the option is worth only 12. Therefore, delta B times 100 is equal to 100, and delta B is equal to 1. In other words, if after 3 years these shares are at 50, Potiphar should be holding precisely 1 share of SJGS. How's he going to get this? Well, he's going to have to borrow 50 gold pieces, and he's going to have to pay interest in year 7, which is equal to 50 times the balance on that loan after 4 more years, when it's multiplied by 3 halves. So he's going to have to pay out 25 in interest. Now, since everything is the same, whether the shares go to node D or node E, I can do the computation for whichever of those is simpler. I find E simpler. Potiphar will pay out 25 to pay off the loan and 12 to settle the option. That would also be the same at node F, but we're trying to figure out the value in year 3, at node B, and $37 in year 7 has to get multiplied by 2/3 to get 74/3. And you may or may not remember from last time, that's what we figured out was the value of one of these call options at node B. So we got the same answer without ever mentioning the probabilities. Okay. Suppose, on the other hand, that the shares stay stuck at 30 after 3 years. Well, you get the idea. This time, he's going to purchase a probably different amount, delta C shares, and say that at year 7, when I go to sell these off, if the shares have gone up from 30 to 50, I get delta C times 50, but I have to pay 12 gold pieces to settle the option. If they go down, I don't have to pay anything on the option, but I can sell them for only 30, and therefore delta C times 20 is equal to 12, and delta sub C is equal to 3/5. So the number of shares that Potiphar should be holding after 3 years depends on how things are going. If this company looks as though it's booming, he wants to own more shares to hedge it than would be the case if it's not doing well. So in this case, he only has to borrow 3/5 of the price of a share, and he's paying the lower price 30. That's just 18. He's going to be required to pay interest on that loan, so the cost of that loan is going to be 18 times 3/2 minus 18, or 9, but those are 9 year 7 dollars. The value of that amount of gold in year 3 is 9 times 2/3, or 6. And you may recall from last time that that was what we figured out to be the value of this option at node C. Now what do we do at node A? At node A, the right hedge is to purchase delta sub A shares. And the idea is you want the position to be the same financially at B and at C. Well, if we go to B, Potiphar owns delta sub A shares, each of which is worth 50, but he is also liable for the consequences of a call option whose value at that time is 74/3. If the shares don't go up in the first 3 years, he's got shares that are only worth 30, but that's okay because now his liability for this option has an expectation of 6, and therefore solving 20 delta sub A is equal to 56/3, and delta sub A is 56 over 60, or 14/15. How's he going to do this? Well, of course, he's going to borrow enough to buy 14/15 of a share. That's 28 gold pieces. And over the first 3 years, he's going to have to pay interest on that loan, which is equal to 28 times 4/3. That's the growth factor for 3 years at this interest rate, minus 1, or 28/3. Okay, now we get to C. He has to pay 28/3, and the expected liability from the option is 6. But to figure this out in year 0 dollars, we discount for 3 years, and we get 28/3 from paying off the interest, add 6 for the remaining liability on the option, multiply by 3/4 to discount, and we get 46/3 times 3/4, and what do you know? That's exactly the same value that we calculated last time in terms of probabilities. So this is the theme of Black-Scholes taken one step further. You can compute the value by working on probabilities. You can work out the problem by talking about hedging, and you get the same answer in both cases. And here's finally what we tell Faro about your perfect hedge. Your perfect hedge is in year 0 by 14/15 of a share. Watch how the Nile and the shares are doing in year 3. If the shares are up by an extra 1/15 of a share, so that your holding is now adjusted to delta B, which is supposed to be equal to 1. If, on the other hand, the Nile is up and the shares are down, sell 1/3 of a share to get your holdings down to delta C, which is equal to 3/5. And what you're going to be learning over the rest of the course is the Black-Scholes equation results from extending this idea to the case where you adjust your holding in the underlying security continuously in order to achieve this perfect hedge.